Delaware Tech, Chemistry 100, Chemistry 110, heat transfer and temperature. So in talking about heat transfer and temperature with substances, it's important to understand the concept of thermal energy. Thermal energy is a quantity that we measure like any other energy in joules, if we're using the metric system or the SI system. And that is really the kinetic energy associated with all the random motion of whatever atoms or molecules you have in a substance. And that movement directly results in a certain amount of kinetic energy, because remember, kinetic energy is based on movement. And this property is what we call extensive, which means if we have more matter, we have more thermal energy. If we have less matter, we'll have less thermal energy. So it depends on how much matter we actually have. Heat is extremely closely related to thermal energy. In fact, the only difference between thermal energy and heat is thermal energy is the energy built into the substance, and heat is the energy that's transferred from that substance or that object to another object. So again, it's measured in joules because it's another form of energy, and it's related to the total energy of the molecular motion, just like with thermal energy, but it's being transferred. So we really can't measure the thermal energy of an object or a chemical. That's very difficult to do. We can only measure it when it's being transferred from one place to another in the form of things like heat. So again, this is another extensive property. It depends on how much matter you have. For example, if I have two beakers and they have the exact same temperature of the water in those beakers, and one beaker has twice as much water as the other, well, the one that has twice as much hot water has twice as much heat energy in it. So there's twice as much thermal energy built into the larger beaker of water than the smaller beaker of water. Whereas the temperature is an intensive property. It doesn't matter if the molecules are moving the same speed in those two beakers of water, they'll have the same temperature, because temperature is really a measure of the average speed of the molecules. It's not exactly the number, but it's directly related to the average speed of those molecules. So temperature is not a velocity or speed. We measure it in degrees, as you already know. And in the metric system, we use degrees centigrade, also known as degrees Celsius, because the person, Anders Celsius, created the centigrade scale. And if we're using the standard international system, the SI system, we would use degrees Kelvin, sometimes written as degree big K, and sometimes written more modernly as a little k. So sometimes you'll see that as well. So specific heat is not to be confused with heat or thermal energy. This is the amount of heat needed to raise the temperature of exactly 1 gram of substance by exactly 1 degree centigrade. And remember, the size of 1 degree centigrade is exactly the same size as 1 degree Kelvin. So you can just say by 1 degree. So the specific heat is really the heat per gram of the material per degree that you're going to change the temperature of that material. So as a result, the units reflect this. The units in the metric system would be joules per gram degree or degree gram, because it's heat per gram per degree. The per for each of those puts it in the denominator. The imperial system, when we used calories, the specific heat version of that would be calories per degree gram, because calories is our unit of heat in the imperial system. And in the SI system, it's still joules, but instead of grams, they use kilograms. So these are all different units. And you'll notice that there's a little k instead of a degree sign. That little k is just the more modern way to represent a degree of Kelvin. Feel free to use the normal degree sign for now. But you might see this unit as well if you're looking in the literature. So the specific heat, remember, is how much heat it is to raise 1 gram by 1 degree. What does that mean? It's the amount of energy you have to pump into a substance to make it go up in temperature. And water is really unusual. Water requires a lot of heat energy to make it go up even a little bit in temperature. And so water specific heat is 4.184 joules per degree gram. What that means is you have to add 4.184 joules or 1.000 calories, those are the same thing, for every gram of water you have for every 1 degree you want to raise it up in temperature. And these numbers look like little numbers, but in the world of specific heat, these are actually considered extremely high values. Water has one of the highest specific heats known. In fact, I can only think of two other substances that have higher specific heat, and they're very oddball substances that you don't usually have at room temperature in everyday life. So almost everything is lower than water. Water is hard to heat up, and when it is hot, it stores a lot of energy in it. And the reason why is water is composed of these individual water molecules that are linked with so many of these intermolecular forces of the highest type of those, the highest energy type of those, which are called hydrogen bonds. Hydrogen bonds are plentiful in water, and every water will form many, many hydrogen bonds with water molecules surrounding it. And while each of these bonds is not worth a lot of energy, there's so many they add up. So breaking water up to make it even move faster requires the breaking of a lot of hydrogen bonds, and this is why it takes so much energy. In fact, that goes further when you're trying to boil water. So now you're not going from cold water, liquid water, to warm liquid water. You're going from hot liquid water to gaseous water, steam. And that requires even more hydrogen bonds to be broken, and that's why it's hard to get water to boil. You have to pump in a large amount of energy to make liquid water warm, and then you have to pump in a large amount of energy to make liquid water that's hot already turn into gas. This is compared to metals. Metals are very easy to warm up, to raise in temperature. It doesn't take a lot of energy to be added to the metal for the temperature to go up. And you know that because when you put a pot on the stove, if you're putting it on the flame and you're adding heat to the pot, the metal heats up very fast. It goes up in temperature very fast. But the water takes much more heat for it to go up in temperature. And in fact, the metal specific heat, if we look at in the joules per degree gram, metals range from about 0.1 to 1.8. Compare that to the 4.184 joules per degree gram for water. So even the most impressive metals are still about 2 to 3 times easier to warm up than water is, and in some cases as much as 40 times easier. So big difference in specific heat with metals. Doesn't take much energy doesn't take much heat or energy to raise their temperature up. So how is this applied? Well, specific heat and heat are not the same thing. Remember, specific heat is a constant for every substance. Every substance has its own specific heat, but any substance can have any amount of heat. That can vary completely, but they are related by a formula. The heat, which is Q, and you can use a capital Q or a small q, one of the few things where you can use lowercase or uppercase for. The Q is equal to the specific heat times the mass of the material times how much temperature change you want the substance to go up. And temperature change, remember, is always the final temperature minus the initial. In fact, anytime you see that delta, that means the change in whatever is written there. So this is change in temperature, and that's how you'd say it, change in temperature. And it's always assumed that anytime you have a change in something, it's always the final value minus the initial value. So you'll notice the units here, Q, heat, is in joules, specific heat is joules per degree gram, the mass is in grams, and the two temperatures are in degrees centigrade, or they can both be in degrees Kelvin, doesn't matter, as long as they're both in the same unit. And when you take the difference, that will still be degrees, and at that point it doesn't matter if it's degrees centigrade or degrees Kelvin. They'll be degrees C because those are the same size degree that you're increasing the temperature. And you'll notice the grams will cancel grams, the temperature degrees will cancel the degrees, and you'll be left with joules for heat. So you take the constant for the material, multiply it by how much material you have, and multiply that by how much temperature change you're really going to change it, and you'll get the total heat. So you can solve this equation if you know any one of these. If you know any four of these five values, you can figure out the fifth value with simple algebra. So let's look at a situation. We're not going to continue the math on this. This is the situation of taking hard, cold ice and warming it up and eventually getting hot steam out of it. Well, what happens here? We have 5 steps. First, we have to warm up the ice to get it to the melting point of ice. And then the ice will melt. And so when it's melting, you have a mixture of the solid ice and the liquid water as it's melting. Then you have, at step 3, you have water, and now you add more heat, the water will warm up. You keep adding heat, eventually the water will hit its boiling point, and then when it hits its boiling point at step 4 here, the water will vaporize to become steam, a gas form of water, and at that point, during step 4, you have a mixture of liquid water and gaseous water, what we call steam. And then you add more heat to this steam, well, the steam is just going to heat up. So let's look at this experimentally. If we do an experiment and we measure the temperature of water as we're continually adding more and more heat, so heat is on the x-axis, temperature is on the y-axis, we're changing how much heat, we're adding more heat, we're going from left to right, and we're watching the temperature of the water increase with time. Well, we get this very unusual curve. Now I want you to look at this curve and you'll notice something right off. It's bent into pieces. And if you count the pieces, you see there are exactly 5 pieces. Well, these 5 pieces match exactly the events that are written at the top here. Step 1 is the ice warming up, so the temperature is increasing. Step 2, the ice is melting. So when you're adding heat to the ice that's melting, so this is at the melting point of water, of ice, you're just changing solid water to liquid water, so you're not actually putting the energy into making the molecules go faster, you're just putting the energy into breaking the ice apart into liquid water, and that requires breaking some of the hydrogen bonds. And then once you get past that, you get to step 3, and now you're warming up the water, the temperature goes up as you add more heat, eventually you hit the boiling point, and now you're going to be boiling the water at step 4, so you're turning liquid water into gaseous water. That's where the energy is going, not into raising the temperature. And then finally, once you have all of it turned into gas, steam, now anytime you add more heat at step 5, you make the temperature go up. So if we look at the 2 plateaus in this, they match the melting point of water at 0 degrees centigrade and the boiling point of water at 100 degrees centigrade. And that's what we would expect to see. And if you look at the regions here, anything below 0 degrees is solid water, ice. Anything between 0 and 100 is liquid water. And anything above 100 is going to be gas, steam. So we have these 3 big regions that are divided by this 5-sided curve that we created. And we know that the first step is the heating up, the middle step is heating up the liquid, and the last step is heating up the gas, and the other 2 steps are the transitions. The melting, going from liquid to liquid to gas, and with that, at that point, it's a mixture of liquid and gas. At first, it's all liquid on the far left of number 2, all solid on the far left of number 2, and eventually it makes it to all liquid, and then once we have all liquid, it can rise up to step 3 and increase in temperature. Then when you get to step 4, the beginning of step 4, it's all liquid, and it's transitioning to become gas in a process called vaporization or evaporation or boiling. And there, again, it's a mixture of liquid and gas until you're all gas at the end of step 4, and now the gas just heats up.